Welcome to our latest video on hydrocarbon properties and cracking. This video is suitable for GCSE students. By the end of this video lesson, you should understand that hydrocarbons are often used as fuels and be able to describe how a hydrocarbon's chain length affects its boiling point, viscosity, and its usefulness as a fuel. You should also be able to describe what happens when a hydrocarbon undergoes cracking, how the process is carried out, and why the process is important. And you should also be aware of the global economic and political importance of the oil industry, as well as its social and environmental impact. Now, in our previous lessons, we've learned that crude oil is a mixture of different substances, and these substances are called hydrocarbons. Hydrocarbons are compounds that contain hydrogen and carbon only. And there are two types of hydrocarbons, alkanes and alkenes. Now, alkanes are held together by single covalent bonds, while an alkene contains a carbon-carbon double bond. Now, in our previous video, we've talked a lot about alkanes and alkenes, and we talked about how they're named and how to draw their structures. So this slide summarizes how we name simple alkanes and alkenes. So if the hydrocarbon has one carbon in it, the name starts with METH, meth. If it has two carbons, it starts with ETH, F. If it's got three carbons, it starts with prop, PROP, four carbons, bute, BUT, five carbons, pent, PENT, and six carbons, hex, HEX. Now, an alkane always ends in ane, and an alkene always ends in ene, ene. Therefore, if I have an alkane with four carbons, 4 means bute, and it's an alkane, so it ends in ane, the compound is named butane. If I have an alkene with 5 carbons, 5 carbons in a hydrocarbon starts with pent, and because it's an alkene, ends in ene, a 5-carbon alkene is pentene. Now, in this video, we're going to be concentrating more on alkanes than alkenes. And this slide shows the first 3 members of the alkane family. Methane has a molecular formula CH4, ethane C2H6, and propane C3H8. Now, all of these are alkanes because they're held together by all single covalent bonds. So we're now going to look at alkanes in a little more detail. Alkanes are classed as saturated hydrocarbons because they contain all single covalent bonds between their atoms. There are no double bonds. If a molecule has only single bonds between its atoms, it's classed as saturated, and if it contains a double bond, it's classed as unsaturated. Alkanes are saturated. And alkanes are fairly unreactive because each carbon already has the maximum number of bonds attached to it. There are no spare bonds. Now, even though alkanes are fairly unreactive, they do undergo combustion reactions with oxygen. Now, a combustion reaction is where a substance burns in a good supply of oxygen. And when you burn an alkane, it will react with oxygen to produce carbon dioxide and water. Now, that's probably no surprise to people because alkanes are hydrocarbons, and a hydrocarbon consists of carbon and hydrogen. And if you burn carbon, you get carbon dioxide, and if you get hydrogen, you get water. So you have to remember that alkanes are typical hydrocarbons in the sense that if you burn them in a good supply of oxygen, they will produce carbon dioxide and water. Now, alongside carbon dioxide and water, you also get lots of energy released. And that's why alkanes are used as fuels. A fuel is a substance we burn to release energy. Now, alkanes are excellent fuels. They produce lots of energy when you burn them, and they burn cleanly without much soot. And alkanes are therefore used as fuels. So methane is used in cookers. Butane, for example, and propane are used as camping gas. Octane is used in petrol. Methane is also used in Bunsen burners and in gas fires. And camping gas such as butane and propane may be used in barbecues, while butane is used in lighters. Even substances such as candle wax are essentially made out of alkanes, and it's therefore important when studying chemistry to be aware of the world's reliance on alkanes and oil as a fuel source. Now, it's also important that you're aware of the environmental impact of burning hydrocarbons. Now, when you burn a hydrocarbon, it reacts with oxygen and forms carbon dioxide and water, along with energy. The reaction is exothermic. However, the carbon dioxide is a greenhouse gas, which means that it traps heat and causes the Earth's temperature to rise. Now, this ultimately is global warming, and global warming has a massive impact on our planet, from ice caps melting to droughts and extreme weather conditions, and therefore it's very important that as a world we reduce our reliance on oil, we stop burning fossil fuels, and we reduce CO2 emissions. To minimise the impacts of climate change, it's important that governments look for alternatives to burning hydrocarbons and fossil fuels. It's also important because fossil fuels such as oil are non-renewable. If they run out, it takes millions of years to replace them. Now, in addition to the environmental impact of the oil industry, you must also be aware of its effect on society and its global economic and political importance. Now, the exam board, the WJC, want you to know that rapidly growing economies in China and India are consuming greater amounts of energy year on year, and crude oil is used to supply that energy, and that is not sustainable in the long term. Because crude oil is a non-renewable resource, takes millions of years to replace it, the growing demand for these fuels will drive prices upwards, and it also will affect individuals' heating and travel costs, but also indirectly it causes inflation and rise in prices in everyday items such as food. So the oil industry is key economically. If oil prices are going up because there is a growing demand for oil, this affects the cost of living in Britain, and it affects society as a whole. And that's what the syllabus is trying to get at when it talks about you understanding political, economic and social impacts of the oil industry. Now, in this video so far, we've looked at the chemical reaction of hydrocarbons and alkanes with oxygen, combustion, and we've discussed alkanes' use as fuels. Now we're going to focus on properties of hydrocarbons, and the properties that we're going to talk about are physical properties, things like boiling points, their viscosity, their ability to ignite. Now, different hydrocarbons that we get from crude oil are made up of different sized molecules, and in our previous video on the fractional distillation of crude oil, we learned that the longer the molecules, the harder they are to boil, pour, or burn. Now, in an oil refinery, long hydrocarbons are broken down into smaller, more useful hydrocarbons by heat and a catalyst, and this process is called cracking. Now, as alkanes are mainly used as fuels, it's vital that you're able to burn them. It's vital you're able to pour them, and it's vital that they have low boiling points, so you can turn them to gas, and you're able to transport the gas conveniently through pipelines. So in an oil refinery, when we refer to cracking as making the hydrocarbons more useful, we mean it makes them easier to burn, boil, or pour. Nobody wants a fuel that you can't transport from one place to another. So an ability for a fuel to either pour or be piped via pipelines is essential. So to illustrate this, we have two molecules. We have decane, which has 10 carbons and 22 hydrogens, and is a long hydrocarbon molecule. And we have methane, which is CH4, 1 carbon and 4 hydrogens, and is a very small hydrocarbon chain. Now decane has a longer hydrocarbon chain, so it's harder to boil, it has a higher boiling point, and it's harder to burn, and it's harder to pour than methane. And decane is a liquid at room temperature, and methane, because it has a much lower boiling point, is a gas at room temperature. So you have to remember, the longer the molecule, the harder it is to burn, pour, or boil. Now, if a substance is difficult to pour, we say that it is very viscous or has a high viscosity. And when we studied the fractional distillation of crude oil, we mentioned a fraction called bitumen. Now, bitumen is made up of very long hydrocarbon chains, and this substance is used for road tar. Now, road tar is a very difficult substance to pour. It has a high viscosity, and its high viscosity comes from the fact it has very long hydrocarbon chains. So this slide shows what happens during cracking. So on the slide we have octane, which is a long hydrocarbon molecule. It's got 8 carbons in, and it's got 18 hydrogens. And if I heat this up to a high temperature and have a catalyst, this will split up into a shorter chained alkane, in this case hexane, and an alkene. Now, you've got to remember that cracking involves breaking down long chain hydrocarbons into smaller, more useful hydrocarbons using heat and a catalyst. A number of different catalysts can be used in this process. However, it's important to point out you will not be required in the exam to name one of these catalysts that can be used. You just have to know that cracking is caused by heat and high temperature. Now, if you look at the overall equation here for this example, we have C8H18 breaking up into C6H14 and C2H4. Now notice that on the left-hand side of the equation we have 8 carbons. So therefore we must have 8 carbons on the right, because in any chemical equation the number of atoms of each substance on the reactant side, the left, and the product side, the right, must be the same. So if I have 8 carbons on the left-hand side, my right-hand side must add up to 8. So C6H14, C2H4, 6 plus 2 equals 8 carbons. And my hydrogens are also balanced. I have 18 on the left and I have 18 on the right. Now, it's very common in exam questions for students to be given an equation that is only half completed. So you will have to finish the equation. So you have to always remember that in a cracking reaction you make a smaller alkane and an alkene. So if I was only given part of this equation and I was given C8H18 goes to C6H14, I would have to work out how many carbons and how many hydrogens would be in the remaining molecule. And I do this by looking at the equation and realizing I must have the same number of carbons and hydrogens on either side. Now, it's also important to mention that with cracking we don't just make a smaller alkane molecule that's easy to burn, pour and boil. We also make alkenes, and alkenes are hugely important to the chemical industry. For example, we use alkenes to make alcohols. We also use alkenes to make plastics, such as PVC, such as polyethylene, such as polypropylene, such as polystyrene. This slide shows the apparatus you would use to carry out a cracking experiment in the laboratory. So I would have a boiling tube, and in the boiling tube I would put some mineral wool soaked with the long hydrocarbon that I was going to crack. So for example, I could be cracking paraffin here, and that would be a saturated hydrocarbon fraction, a long chain molecule. And in my boiling tube I would have a catalyst, which could be things like a piece of porcelain or aluminium oxide, which acts as a catalyst. And this boiling tube is clamped, and it has a delivery tube that goes into a trough of water, and I then fill up a test tube full of water. I put this over the end of the delivery tube, and during the experiment I heat up the catalyst, and the paraffin or the long hydrocarbon molecule that I'm cracking turns to vapour and passes over the catalyst. Now when this passes over the catalyst, it breaks up into my alkene and my smaller alkane, and I'm able to collect the gases that form in a test tube, and if I test the gas, they're easy to burn. And because an alkene is present, I can add some bromine water to it, shake it up, and the bromine water will decolorize. Now, bromine water going from orange to colourless is a test for an alkene. So in this cracking process, I've made a smaller alkane that is more useful and an alkene. And adding bromine to my test tube confirms the presence of this. Now the video clip you've just watched was recorded by the Royal Society of Chemistry, and if you check out their website you'll find a great range of resources to support students studying both GCSE and A-level. So now let's test your understanding of hydrocarbons and cracking with some practice questions. So here's our first practice question. So for question 1, there are 4 hydrocarbons drawn for you on the slide, and the question is asking you to decide which one has the highest boiling point and which one is easiest to burn. And for question 2, the question asks, petrol contains hydrocarbons 8 carbons long, while diesel is made up of hydrocarbons that are 14 carbons long. Which is easiest to pour? Is it petrol or diesel? Pause the video, read for the question, have a go at it, and then we'll go for the answers. So for question 1, you have to remember that the longer the molecule, the harder it is to boil, the harder it is to burn, and the harder it is to pour. So the one that has the highest boiling point here is going to be compound 3, because this compound has the longest molecule. Long molecules mean they're hard to boil, so they have the highest boiling point. Now that compound is actually called pentane, but you weren't asked to name this in this question. Now the compound that is easiest to burn is compound 2, because that has the shortest molecule. That compound is methane, and it's easiest to burn. Now for question 2, you're asked which of petrol or diesel is easiest to pour. Now remember, the longer the molecule, the harder it is to pour. So the longer molecule is diesel, so therefore petrol is the easiest to pour because it has the shortest hydrocarbon. So now here's question 3. Now this question is in 2 parts, 3A and 3B. And here's part A. Read through the question, pause the video, have a go at it, and then we'll show you part B. So here's question 3b. Once again, read through the question, pause the video, have a go at it, and then we'll go through the answers to part A and part B together. So here's the answers to question 3a. So the first thing you're asked is to complete the following symbol equation for the reaction taking place. Now they've given you decane, C10H22, and they've given you the alkene that's formed, C2H4, and you have to realise that you need 8 carbons and 18 hydrogens for the equation to be balanced. So it would be C8H18. Now it's asking you to name the process, and that process is cracking. So there's 1 mark for each of those. Now for question B, you've been shown a piece of apparatus to investigate the products formed when ethene is burned. And the question is asking you to state what you would expect to happen to the lime water when you burn ethene. Now this question is all about you understanding that when you burn a hydrocarbon, an alkane or an alkene, you get carbon dioxide and water. So lime water is a test for carbon dioxide. So the lime water would go milky or cloudy as carbon dioxide is formed. So here's the last question we want you to have a go at. Read through the question, pause the video, have a go at it, and then we'll go through the answers. So let's go for the answers to question 4. So for part 1, it says complete the equation for this reaction by adding the formula of one other product. So C15H32 splits up into C3H8 and C2H4, and there's 2 lots of that. So if you add up the total number of carbons that they've drawn for you on the right, that adds up to 3 carbons plus 4 carbons. It adds up to 7 carbons. So you need 8 carbons in total in the other product, and they've told you you've got 2 lots of this product. So therefore it must be C4. 2 lots of C4 would give you the 8 carbons you need. Now for the hydrogens, you need a total of 32. So they've drawn C3H8 and 2 lots of C2H4. So that gives you 16 hydrogens in total. So you need another 16 hydrogens in this molecule. And remember, you've got 2 lots of the molecule, so it must be 2 lots of C4H8, because 2 lots of 8 equals 16, and that's how many hydrogens you need. Now for part 2, you have to give the reaction conditions used in this process, where you need a high temperature and a catalyst. You need both to get the mark. And for the last part of the question, it says give one reason why it's important for oil companies to carry out cracking. Well, you could either say that small fractions are more useful, in other words they're easier to burn, boil or pour, or you could say there's more demand for smaller fractions, because that's essentially saying the same thing, or you could say that cracking produces alkenes. Any one of those gets you the mark. So by the end of this video lesson, you should now understand that hydrocarbons are often used as fuels, and be able to describe how a hydrocarbon's chain length affects its boiling point, viscosity and usefulness as a fuel. You should also be able to describe what happens when a hydrocarbon undergoes cracking, how the process is carried out and why the process is important. And you should be aware of the global economic and political importance of the oil industry, as well as its social and environmental impact. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @Radachemistry.